All right, let's go through some examples of double integrals. Now, what is a double integral? So if we have an integral of a graph with two axes, here's our f of x, label my axes, f of x, the integral from one x value to another x value is the area under the curve. All right. Now, a double integral would be useful if we have three axes. Let's say that for some region on the, let's call this the x, y plane. Make this z. We have some 3D surface, right? That comes out from this region here at the bottom. Okay, so in a double integral, instead of finding the area under the curve, we're finding the volume under the function, right? We'll call this f of x, y. Okay, so in the first one, we have a single integral. Second one, we have a double integral. In the first one, if we wanted to find the area under the curve, what we would be doing is we would be taking lots of little tiny rectangles, right? Adding them all up together. Small the rectangles get, the better that your approximation gets. In calculus, those rectangles approach zero. Now, in a three-dimensional situation, we actually have to take an integral in both directions, right? We slice it up this way, right? And say that we take that slice and we look at what it looks like over here from a side view. X-axis, Z-axis, right? We have something like this. Okay, well, now we have this little sliver. Well, how are we going to figure out the area of that? Well, the same way that we did up here in the single integral. So we do a single integral for this whole part, right? And then that becomes part of our second integral, which we're going to do in this direction, right? So we're going to repeat that process over and over again for the entire volume of this function. So we have our first integral, then we have our second integral. Okay. So let's start out with a very easy double integral. D. Okay, so this is how you'll see a lot of the integrals start to be written out, being written out at the beginning, right? A is simply the area of the the bottom rectangle, I guess, in this case, that that the uh, that you want to find the volume of the function under. So let's go ahead and well, first we need to define what the rectangle R is. So R has some set of x coordinates, right? We'll say that it goes from 0 to 3, we'll make it 4, and that's its x side. And on the y side, it goes from 0 to 6. All right, let's graph what this looks like. So on the x-axis, we go from 0 to 4. Let's say that 4 is right here. Great. And then on the y-axis, we go from 0 to 6. Let's say that 6 is right here. Okay. So we have a rectangle. And at any point in this rectangle, we have we this is the domain of the function. And if we look at what the function is, our function is simply 3, right? So from that we have f of x, y is equal to 3. So what does this look like? In our area where we have x and y, simply we go up on the z-axis by 3. It should come out looking like a rectangular prism. Great. And it has a height of 3. Okay, now you know how to calculate the volume of that. It's pretty easy. But we're not going to do it in a typical geometrical way. Instead of it, we're going to do it through integrals. So let's rewrite this integral that we have up here. To make sense for this graph. All right. Now, what do we know about dA? A is down here. dA equals dx times dy, right? Because we have our dx is this area right here, or this length right here, and dy is this length right here. Right, we'll call that dA. Okay, so now that we have that, we can rewrite our equation as 3 dx dy. Now, what are the limits of these integrals? Because they're not indefinite. We have definite integrals here, right? Just like up above when we were finding the area under the curve, right, or the volume inside of the shape, they're definite integrals. We need to have a starting point and a stopping point on both the x and y axes. Okay, so which one's which? Dx is part of this integral. Dy is defined by this integral. Okay. What are our limitations on dx? Well, dx, if we look over here, starts at 0 and it stops at 4. Okay. So 0 on the bottom, 4 on the top. Okay. Y starts at 0, ends at 6. Okay. So put a 0 on the bottom, a 6 on the top. Now, this should be pretty simple. This is actually pretty simple to solve from here. What you do is you solve the integral on the inside first, and then you solve the integral on the outside second. Okay, so let's go solve the integral on the inside. Integral of 3 is just 3x. So we have equals 3x from 0 to 4 equals 3 times 4 minus 0. So we get 12. That's the area under the curve in the x direction. Now we want to find the volume, so we need to also extrapolate that across the y direction. So let's plug this back in to our second derivative here, which goes from 0 to 6, and it's dy. We plug this answer inside here, take the derivative, which is very simply 12y 6, 0, okay? Okay, 12 times 6 equals 72. We're not wrong. And that would be your answer. Now let's go check that against our picture that we drew up here. Okay. We have 4 times 6, 4 times 6 times 3. And oh, my calculator. Check this, 4 times 6 times 3 equals 72. Now, this was fairly simple because inside of our double integral, we just had 3. But what if we actually had a real function of x and of y that we needed to solve for the area under? Let's try an example of this. All right, let's try an example where we actually have a function. All right, so this is our function that we're working with. Now, remember that in the rectangle problem, that these numbers represented our y bounds, right? These numbers represent our x bounds. But in this case, for our x bounds, it makes sense. We go from 0 to 4. But from our y bounds, we go from 2 to the square root of x. Huh. Okay, so let's start with the bounds on the outside. We're going to go ahead and graph what these bounds look like. X, Y. Okay. So our x bounds are super easy. We go from 0 to 4. Awesome. Now our y bounds, we know what our top bound is. So let's go ahead and just throw that on here. We have 2. Now let's actually draw the line for these bounds. All right. Now we have one left to draw, which is square root of x. What does this mean? Well, y is bounded by 2 and the square root of x. Let's look at x's bounds. X is bounded by 0 and 4. But what these actually are is these are equations for lines. This is not just 0 and 4. 4 is x equals 4. Then 0 is x equals 0. Okay, so what does that mean this is? This is y equals 2. And this is y equals square root of x. Right. Okay, well, we know what that looks like. We know what a square root graph looks like. We can go ahead and plug some sample values in for these numbers. So we have 1, square root of 1 is 1, square root of 2 is square root of 2, square root of 3 is square root of 3, square root of 4 is 2, right? So it's going to end up intersecting right there. And we can go ahead and draw this sideways parabola. All right, so let's go ahead and label this line right here, y equals square root of x, right? Okay. This was y equals 2, this was x equals 4, and over here we have x equals 0, but that's just the y-axis. So between all of these, we have an area. We have an area that's greater than 0 and less than 4 for x, and we have an area that's greater than y equals the square root of x and less than y equals 2 for y. Let's go ahead and color that in. Okay, we're going to call this area R, right? And R is described by a couple of equations that we already figured out. So R is the area where X is greater than or equal to 0 and greater or less than or equal to 4. And Y is the area where Y is less than or equal to 2 and greater than or equal to the square root of X. All right. So what do we do with all that? We're going to use all this information to start computing the area under the, well, we're going to use this to compute the area of this three-dimensional function. Now, what does this three-dimensional function actually look like? Well, let's figure this out. Let's say that this is your x-axis, that this is your y-axis, this is your z-axis. So our function, we came up with the area that we came up with looks a little something like this, right? Now, f of this axis is z, or f of x comma y. Now, what is our f of x, y? That would be this nice equation right here. So whatever that spits out is our third dimension of this function, right? And it might be, something, I don't know. Who knows what it looks like? But it's that cutout. Call this R down here. Okay. So we want to figure out what the volume of whatever this shape is. Okay, so let's start taking our double integral. Now that we know what we're looking for, let's start actually doing math. So remember, we want to start by taking this integral, and then we want to take this integral. So let's go ahead and just grab that. All right, so how would you solve this integral? You probably wouldn't solve it like this. Reason being, if you do u substitution, we run into a dead end, which I can go ahead and walk through. So let's set u equal to 4 plus y cubed. That means that du is going to be 3y squared dy. This means that dy is equal to du over 3y squared. Now, if we try to substitute that back in here, then what we get out of that is some set of limits for the function 1 over u du over 3y squared. Now, this isn't going to work. The reason being is we still have a y left over down here. You could find the integral of this, but it would take a long time. There's actually an easier way to go about it. What do I mean by that? What I mean by that is that we can actually flip-flop these dy and dx around. Right? If you remember from a rectangle, all that dy and dx are is this side in dx, actually this side would be dx, and this side would be dy. No matter which way you multiply them together, you could say dy dx is equal to dA. And you could also say that dx dy is equal to dA. So why don't we just switch these two integrals around? Now, this is where you want to be careful, because you can't just give these whatever values that they already had for your x bounds and your y bounds. You can't just put 4 and 0 here. This doesn't work. What you have to do is look back up here and say, okay, what are my x bounds actually? If we're going to put x first. Sorry. What you have to ask is, now that we're looking at y first, we're going to look at whatever function comes on the outside first. So y goes from 0 to 2. We can see that, right? We're going to iterate along y. We're going to go 0 to 2. And then the inside, for x, we're going to look at, okay, as we're going from 0 to 2, at any of these points that we pick, right, our x values are going to be somewhere in that range. So what is that range? The lower bound is 0, right? But the upper bound is this curve. Now we can't say square root of x, because if you remember, these are equations for whatever the variable is, so we can't say x equals square root of x. Instead, we look at that equation and we say x equals y squared, right? You're just solving this equation right here for x. In fact, let's go ahead and rewrite all of these as equations for now. X equals 0, y is equal to, y equals 0. Okay, these are our new bounds. Let's write these bounds up here with this graph. Okay, or we'll do y first. And x. All right, now let's try integrating it this way and see if it pans out this time. So our first integration is going to be this right here. This comes out to, because y is just a constant in this case, dx, we would take this as a constant, just add x onto the end, right? And we're going from x equals y squared, x equals 0. So we can substitute this in, and we get 1 over 4 plus y times y squared minus 0, which then is going to come out to, or sorry, this has a cube on it. Okay. This comes out to 1 over y squared over 4 plus y cubed. All right, okay, so we got through the first integral. Now we plug that into the second integral. Of y equals 2, y equals 0. We have y squared over 4 plus y cubed dy. Now let's try u substitution again. And this time, I think it's going to work. U equals 4 plus y to the third du equals 3y squared dy, which then means that dy is equal to du over 3y squared. All right, let's substitute these back into this equation. So for our limits of our definite integral, how we determine them is they're not going to be 0 and 2 anymore. Instead, they're going to be whatever 0 and 2 would be after we plug them into u. So we're going to go ahead and do that. We're going to say 4 plus 0 to the third power and 4 plus 2 to the third power. Now we have y squared over u, because u substitutes in for 4 plus y cubed. dy turns into du over 3y squared. Okay, let's simplify this. 4 plus 2 to the third is 4 plus 8, which is 12. 4 plus 0 to the third is 4 plus 0, which is 4. Then y squared on the top cancels out with y squared on the bottom. So we get 1 3u du. This should be really easy to take the integral of, because you can actually pull the 1/3 to the outside of the integral, which gives you this statement. And we know that the integral of 1 over u du is just going to be natural log of u. Let's go ahead and substitute in 12 and 4. We know that when we subtract natural logs, we can divide the insides of the logs. Four, which then simplifies to natural log of 4 is 3 divided by 3. That's your answer. All right, that problem went pretty slow, but let's do one more. Now that we know what we're doing, this one should go much faster. All right, let's start by graphing it, same as we were doing before. So on the y-axis, we go from 0 to 8. We got 0 down here. Let's put 8 up here. And then on the x-axis, our bounds go from 2 on the upper bound, and then our lower bound is y to the 1/3. And that's x equals y to the 1/3. So that graph ends up looking like a little something like this. Keeps going that way, keeps going this way. All right, let's draw our lines. Area. There's all this stuff right here. call that r. All right, so let's go ahead and write what our bounds are. In this case, we have y is less than or equal to 8, greater than or equal to 0, x is greater than or equal to the y to the 1/3, less than or equal to 2. All right. Now let's go ahead and look at what happens if we reverse the direction that we look at our bounds in. So let's look at x first. X, if you just look on this axis, is very plainly between 0 and 2, right? Which means that now y has to interpolate. Y has to interpolate for any x value between 0 and whatever this function is. So 0, and y is between 0 and whatever this function is, but it's a function of y now, so we need to solve this function for y. So x equals y to the 1/3, then goes to y equals x to the 3rd. So y is less than x to the 3rd. Which one of these sets of numbers would you rather work with when you're taking limits and doing this? Just from looking at the two of these, I'd rather work with x to the 3rd than y to the 1/3. So that's what we're going to do. We're actually going to flip our integrals before we even start. We're going to say that this is equal to e to the x to the 4 dy dx, flipped our integrals. And for dx on the outside, we plainly had these down here, so we went from 0 to 2. From dy on the inside, we went from 0 to x to the 3rd. Okay. So this is what we're going to work with. Now for actually taking the integral. So remember again, we start with the inside one, then we work the outside one. Integral from 0 to x to the 3rd of e to the x to the 4th dy. Since there's no y components inside of here, this is all just a constant. So this is just e to the x to the 4th times y from y equals x to the 3rd to y equals 0. Substitute that in for y. We get x to the 3rd minus 0, which is then just x to the 3rd ex to the 4th, which then goes back into our second integral. To the 3rd ex to the 4th ex. All right, integral of this So we can do some u substitution now. Let's say that u is equal to x to the fourth. Because we know what e to the u du will be, is just going to be e to the u. So that's where we want to end up. Du is 4x to the third, right? Dx, okay. So therefore, dx is equal to du divided by 4x to the third. Substitute these back in. You get, oh, remember that we need to change our bounds based off this equation right here. So we have 0 to the fourth and 2 to the fourth. We have x to the third, e to the u, and the dx becomes du over 4x to the third. All right, let's simplify this. 2 to the fourth power is 16, 0 to the fourth power is 0. X to the third up here cancels out with x to the third down here. So we just end up with e to the u du over 4. Okay. And we can actually pull that 4 to the outside. It's 1 over 4. And that's easy to solve for. Have times 16 0 is just equal to 1/4 e to the 16th minus e to the 0. So then simplifying that, we get e to the 16th minus 1, no, down here, minus 1 over 4. And that is the answer. I hope me walking through these problems helped you out a little bit. If it did, please like the video. If you have any constructive criticism for me, because this is my first math video, then let me know. I look forward to making more and better videos in the future, so stay tuned.